To welcome you to this presentation of 3 secrets to successfully managing product development projects. This is a shortened version of a presentation that was made to the Chicago and Cozyland chapter as part of the fall 2017 tutorial series that that particular chapter runs. Anyway, it is a consolidation of several points that I have found extremely useful in over 35 years of product development and innovation on demand at work. So I'd like to share that with the community, and if it's helpful, please consider sharing it further and sending me notes on anything you might like to hear that's a follow-up on this or other topics. So let's go ahead and get started. The first secret I'd like to share with you is that the universe always wins. Reality is simply reality, and if there is a nature to the task you are doing that requires that you introduce something new, if you don't use methods that are capable of introducing new things, you're going to fail. And that has nothing to do with how smart the people are or how well-resourced they are or how popular the book is whose methods they're copying without fully understanding context. The secret is they're not honoring the nature of the task itself. So in developmental work, it's always true that no matter what you're doing, at least some part of what you're developing doesn't need to be developed. It's a piece part, a bracket, a bolt. Perhaps it's something as significant as an entire facility or transportation infrastructure you can reuse if you're simply wise enough to recognize that. The point is, if you can distinguish project tasks based on this very primary and fundamental difference of do they require something new or response to a variable somewhere inside or outside the system? In other words, do they have to adjust, or are they fixed and thus something you can just simply go execute? If you want to think of these as development and production or constants and variables, there are many analogs that are familiar. I'll probably find myself just flipping between them as we go through the presentation. But recognize we're talking about two very fundamental states that are mutually exclusive from each other. Something that's constant and anchored in the past, or something that's a variable that will be determined based on rules you establish now but will be revealed in the future at some outcome point. Anyway, we want to assign appropriate methods to each one of these circumstances, and when you do that, you'll find that your results improve exponentially, because not only do the appropriate methods serve to function better in that particular type of task execution, the penalty for using the wrong method is actually quite severe, and that's one of the things we'll talk about as we go further in this presentation. And to do this, you really need a different view of work. The kind of macro level that there are giant tasks that design does that are all creative, and then it gets sent to engineering that is sort of a mix of creativity and hard rules, and then it goes to the factory where variance is evil and the rules are 100% in place until you make decisions to do step functions and improvement. There's always continuous improvement and there's always response to variability, but different areas have different kind of macro views of the work. What we're going to do is take a much deeper dive. So if you want to make a comparison, this is a little bit like looking at rocks versus going into quantum mechanics or quantum physics. We want to think about the very fundamental, almost subatomic level of all effort, regardless of its market, regardless of the scale. It doesn't matter whether you're building a birdhouse in South America or whether you're trying to put a satellite in orbit. There's going to be a mix of things that you can reuse and stuff you have to introduce. And those are the two primary categories. On this slide, they're called creative and repetitive. You can substitute any variables that are familiar to you. The big difference is one is constant, one is variable. These are isolated, so think of these as being very primitive, almost the pixels that define the image of the effort that exists within reality. Each pixel is either a creative pixel purely or it's a repetitive one purely, but they can change states. So they're isolated, and the bridge that connects these two states, you can think of simply as lock and unlock. Lock, naturally, is going from a creative to a repetitive state. We're giving up the freedom of movement. Unlock works the other way. We're taking something that was previously defined to a build-to-print standard or other reference, and we're saying it's now okay to change at least some portion of that and see if we can do a better job. So, all real work is a hybrid. It's partly developmental, where you're discovering needs, creating solutions, responding to internal and external variability, losing sleep, but having a great time building something wonderful and new. And it's partly defined, where you're reusing proven solutions, trying to control internal variability for efficiency. You're vulnerable to external variability, so you're losing sleep worrying about that. But if you assign this second category of work to competent people, and they have the ability to refine their processes over time, it's virtually certain that it's possible to do it better and better each cycle and get to a point where you can trust the defined execution elements and you can concentrate then on the work that is developmental, where obviously there are more uncertainties to be managed, and therefore intelligence is more valuable within the organization as opposed to repetitive execution. Robots are the perfect solution for the defined spot. A massive interconnected brain would probably be the best one on the developmental side. We may be getting to that with AI and human interaction, but for now, just distinguish these two types. Recognize that whatever image, whatever shade of gray that you may perceive on an individual project is a combination of these two very primitive, very fundamental states that you are perceiving as gray. The dot is either black or it's white. The image of the lion or whatever it is you see in newsprint appears gray only because of your resolution as you examine things. If you dive deep enough within the nature of every task, even this conversation that we're having right now depends on a constant of having previously established a body of language and the understanding of the words so that some fraction of intent can be communicated to the recipient. But it's also hopefully drawing on something that's variable and real at this moment, which is my sincere desire to communicate ideas and see if I can do that effectively with an audience. It's the difference between hearing a recording and being in a live performance. Anyway, you're dealing with a mix of opposites here. The repetitive tasks strive to eliminate variance. Creative ones are meaningless without it. Now think about this for a second. If you spent 30 years of your career managing a factory where every single task you did, every single idea of good or better had to do with finding and eliminating variance. The idea that there's nothing better than perfect, but you want to get as close to perfect as you can every single time, variance works against that, so go chase it down. Very logical, very sound, ton of great methods out there, tons of professionals who are very good at it. The problem is when you take that logic, those instincts, that drive on the right-hand side of the road versus left-hand side of the road instinct set, into the land where you have to adjust to things or introduce something new. When you go outside of the factory into the design studio or into the customer service interaction or the sales interaction or the customer support interaction following the sale, you find a degree of variability inherent in the nature of the task itself that is not managed or suited by a fixed and constant process. And we use terms like empowerment to tell people that they should follow the process but then do the smart thing, and then we beat them up when they spend a nickel more than what the process costs. And they learn very rapidly that the process is safe, they can hide behind it, and they can then find themselves doing incredibly stupid things and simply blaming the process. Doesn't always work that way, but it does often enough to pay attention to that, maybe a little bit over the top example. Anyway, the repetitive tasks are going to benefit from direction and control. If it's something that's been done before, find someone who's very good at doing it. Tell them, hey, I need this done again. They go, yep, got it, and away it goes. Creative tasks, though, are different. You need direction. You need somebody who understands the process of getting an idea from the mind into reality, but they then need some freedom. They need to understand the process. They need to understand some definition of good that they are pursuing. And then within the envelope that's created by those constraints, they should have as much freedom as possible to explore the combinations, this very rich simultaneous equation that the human mind is much better at managing in many ways than so far we've at least done with software and hardware systems. So anyway, how fixed is fixed? We're going to spend a couple slides here talking about just the nature of when we label something as fixed and we say, hey, we can trust that, it'll be great. It really is potentially theoretically permanent, except in reality, it's always a relative term. What you end up with is fixed is at best temporary. The behavior of a tire is different when you first buy it than when you have 1,000 miles on it than if you try to get 100,000 miles out of it. Certain things, though, are often very arbitrary. How fixed is it? Well, a fixed interest rate that varies periodically with a reset is not really a fixed interest rate. It's an adjustable rate by a creative name. Anyway, the idea is fixed is never perfect. And you need definition to define what fixed really means, over what time interval. I worked on a neutrino detector project for the South Pole where 5 nanoseconds was a significant amount of time because it affected the resolution and the ability of the instrument to meet the science goals. So in that case, anything that had a lot of drift, as in milliseconds, was an enormous impact on the system. In other contexts, that would be completely meaningless. Anyway, against what measurement reference? How do you know this stuff? What's the traceability to it? What allowable error? So anyway, the idea of fixed is complicated, and this is the essence of manufacturing, of trying to get all of these things under control and retain that control in spite of external variability. When in doubt, call it a variable. And the reason for that is it causes you to respect the potential complexity of the task and bring methods that are capable of doing not only a fixed solution, but responding to variable circumstances in order to end up with the fixed output that you were originally seeking. So we need to talk a little bit about half-life. I mentioned that fixed is kind of an artificial state. Continuing this analog to the physics community, you have to introduce energy in order to fix things. You have to spend a lot of time and energy getting those build-to-print drawings through review, detailed, checked out, confirmed, then converted into manufacturing processes, test run, lockdown, machines adjusted, tuned, everybody knows what to do. And once you really got that going, you can't just trust it to stay stable forever. You have to continue investing energy to maintain it. So fixed is inherently unstable, and it's inevitably going to decay back into a variable. That can either happen by choice if you make the decision to unlock it when you're seeking a replacement or a renewal of a particular product line or feature set. You can do it through quality shortfall, which is the scary way. This happens when you're losing control and things are happening outside your performance indicators, which continue to look good, but result in quality defects that then make it to market and in some cases are really critical. Examples would be the primary interface and function of an online software package is working great, but somebody isn't smart enough to encode the hash or hash the keys on the system, and it makes it vulnerable to a 90 million account hack or something like that. Those are the kinds of quality shortfalls that are extremely expensive but result from an artificial sense that you're controlling everything when in reality you are not. Anyway, you can also end up with customer insurrection as a result of that, and sometimes external redefinition. But the key is the half-life of fixed is very rapid, which implies that you need then a monitoring agent that is able to tell how long is this safe and at what point do I need to treat it as a variable, and for some period of time examine where the new fixed state should be and then reset it. We do this all the time with circuitry. We call it phase lock loops. When it's in electronics, it's a governor in a vehicle. There are countless names for feedback loops like this, but it only is possible if you honor the fact that things will decay and you have to put a mechanism in place to avoid that. Moving forward, variability is best thought of as a bubble. Instead of being a single hard data point, this is a cloud in which a solution can appear. And the size of that cloud gets larger with the number of variables that are at play. It gets smaller as you get closer and closer to the point where convergence and a single solution emerges. This is a region in which a data point may exist. When you are done, one will emerge from that region, but until that point, you don't know what's inside this bubble. It's bounded by limits and interactions. It's internally as unconstrained as you can possibly make it. This is a microenvironment that you have created for the specific purpose of nurturing an idea into reality. It has the right temperature, it has the right breeze, it has the right everything you can possibly give it, including all of the necessary skills and, as much as possible, seamless interaction ability from team members as possible. So you're basically trying to create an environment that is productive for bringing ideas into reality. So there are two transitions that we've talked about. The little graphic on the side here brings back the fixed and the variable in the black and white context, but it now shows the unlock in the upper right and the lock in the lower left. We go from a fixed state to a variable state through the path or through the action of unlock that's in the upper right. The reverse works the other way. So two states give rise to two transitions, a lock and an unlock. These are mutually exclusive. You're not obviously doing them both at the same time. Unlock is potentially lossless. It has the potential to remember everything you did before if the organization invests in honoring the value of that information and capturing the subset it sees value with. It's certainly possible to throw things away when you unlock. An example of that would be forgetting the knowledge about a machining or a tooling process that may have been developed over 5 or 10 years simply because you're going to use a different material later, and then you have to go rediscover the same basic knowledge of entrance angles and other kinds of things for particular cuts and seals. Anyway, this process is greatly enhanced by good documentation. Continuity of team members is immense because no matter how good your documentation or high fidelity the engineering models may be, there is a level of understanding that is still really just maintained only in human minds, and that is primarily a memory of the interactions that exist or are possible or have been considered in the past between team members, and those are things that very seldom make it to the documentation. A lot of that also gets stored in the organization. You can capture a lot of that and keep carrying it forward through mentoring and individual training, particularly if you have continuity and a subject matter expert or a guru or an evangelist for the ideas that's maintaining that history and building a set of acolytes over time. Some of the greatest cultures I've been around have been built from that. Sandy McDonald, McDonnell Douglas Corporation. I thought what Norm Augustine did at Martin Marietta Corporation was extraordinary. I loved what happened from the Galvin family with the old school Motorola. But anyway, unlock is potentially lossless if there's a value of the knowledge and recognition that it's something you want to carry forward. All of the cultures I just mentioned, all of those leaders whose names deserve to be recognized as American heroes, all respected how much information there is even when you decide to move on to the next thing. So they kept all of it as a resource for the organization. Again, the fundamental basis of a skunk works. So anyway, unlock is an investment. You change the status of something from safe and stable to uncertain only if you expect to get a benefit from it. Do I unlock it so that I can take better understanding of needs and produce a superior solution? Do I unlock the current solution so I can see what else I could do or what a competitor might throw at me within a year or two? Do I simply improve the means of accomplishment? Do I look at it and say, why am I mailing these things? Is there an electronic distribution or a cloud solution that might be just as effective and perhaps even more valued by my current client base? So a perfect unlock transition would open 100% of the potential value that exists within an opportunity. You can think of that as how much gold is really within that Colorado mountain. If you could actually map it from space and had a perfect 3D image of where is the gold, how much of that can you really get? Well, not all of it is economically recoverable, and there's a similar factor that takes place in program project management, innovation development by any name. But you're only going to capture a few percent of the total opportunity with any one of these shovel bites you take in an individual project. Even a Microsoft or a Google is still digging away at one corner of the mountain. They have not come close to removing all of the gold associated with the space they've opened. So the hard part is it's really difficult to let go of what you've done in the past and all of the habits and all of the methods and all of the infrastructure. Imagine you're a cab company that has hundreds and hundreds of fleet vehicles. You've got an entire team of really professional mechanics and maintenance people. You've got garages all over the place. You've got spare parts. Your people know how to deal with all this stuff. It's very difficult for you to consider that you're not really in the vehicle industry, you're actually in the transportation industry, and that someone else can come along and remove your entire fundamental basis for existence, or at least compete with you very effectively, and own none of that infrastructure. So anyway, those are the biggest blind spots in most of the projects or program efforts I've been part of, are the lack of vision at the beginning. If the vision is good, there's usually a technical means, if not now, relatively soon, to bring that into reality. And of course, it's hard to manage a lot of simultaneous variables. That's the reason it's very uncommon to see a totally new transport device introduced. There are always derivatives or combinations of something that have been seen. It's simply too difficult to take on a simultaneous equation with a million terms and no givens at the beginning. There's just too many iterations usually for an economic solution. There are cases, though, where you think about human genome or cancer research or others where it is worth the national investment in the level of skill set, tools, expenditure of lifetimes of brilliant creative talent in order to make these accomplishments on behalf of all of us. So moving along, the ROI on an unlock can be thousands of %. A decision to do something differently or to view the market differently or to remove the past blinders or weights that you've carried that were useful in the past but are harmful now. These are the biggest, highest value ways to unlock disruptive innovation that I've ever encountered. Lock is how you capture the stuff. Unlock is how you create the opportunity. Unlock is easy. It's real easy to go in and say, hey, rules are gone. So when you release rules, it's almost like you're moving downstream with entropy. You've got the wind blowing behind your back. This is why it is extremely rapid when a process standard or an industry begins to decay and move to a new model. That decay can take place very rapidly because an entire community of users are unlocking their past decisions and freeing up new ones as a result of seeing the world differently. There's a lot of energy released when those old bonds are broken. The challenge is controlling the chaos that results from the release of all of that energy. You unlock only the subset you want to, if possible, but there's a lot of interactions between the subsets you unlock. That one simple software change that everybody with experience dreads someone saying or asking of you is difficult not because the line of code is hard to change, but because all of the interactions between that line of code and perhaps millions of others are not as well understood as we'd like, and sometimes bad things happen that we don't have control over, and we find those only in test or operation. So the key is to unlock as small a subset as you believe represents the section of that gold in the mountain that you want to go tackle with a shovel bite, and then not lose control of the other areas. Basically, you want to focus on where the value is. A Pareto principle from manufacturing applies here, except we're trying to unlock the parts that have potential for us to move forward. Anyway, lock captures gains, but it's very lossy. So we use lock when we decide, having looked at 20 different ways that we might produce our widget, that we're going to do just one. And a perfect lock transition would retain 100% of the knowledge about the one we're keeping, but often a few percent is very much more common. It's hard to squeeze all of the variability out of tasks. Sometimes when we make choices, we're making choices between two paths of variability and not a final solution at that stage. It's hard to comprehensively define everything and capture all of the aspects of it. That's a basic part of system engineering. Lock is particularly difficult for other reasons, though. It requires the buy-in of participants. It's very easy for everybody to say, hey, let's figure out where we're going to hold the event next year. That's exciting. But now you got to get everybody to agree, and that's hard because that requires decisions. People are much better at talking and expressing opinions than they are at reaching decisions in most cases, because it requires a trade-off between things that they want. Someone wants it to be close to home. Another person wants it to be close to existing infrastructure. Somebody else wants to reuse a place that they've used in the past. There are great arguments for all of those. It's just very difficult to reconcile them unless you have some mechanic or analog for doing that. Again, back to the requirements process within systems engineering. There's one winner and many losers. So just the stack of odds are against you. So if each one of the 20 ideas in the room has an advocate, there's one that comes out as the winner, and the other 19 people in the room have to suddenly shift, or at least shift as rapidly as possible, from advocating their idea in open competition to the idea that wins, and acknowledge, well, my idea wasn't any good, that was the one that wins, and go on. It isn't as simple as that, but that's the psychology that often comes up for people, and it's very difficult to get that consensus. It takes time, and the confusion during the interval until that comes clear is an expense to the organization that can be addressed. So lock is inherently unstable. Even if you think people agree on it, you have to keep converging that, because there is a tendency for the people who had the number 2 idea to keep looking over your shoulder and say, well, you know, if you'd gone with my idea for a widget, you wouldn't be running into the supplier issue right now, and maybe it's not too late to change. So it's almost what happens in a competitive procurement environment, that vested interests continue to retain those interests until some outside force moves them off of it. So it's hard to define and enforce lock. In the manufacturing world, it's relatively easy to create a build-to-print spec and identify a controlled source and manage that through the processes. But with ideas where you're going from all of the ways the software could be defined to the single way it will be built, there's no requirement structure in the world or wireframe that captures everything that was in the minds of the participants. So there's always going to be some uncertainty, and that means you have to keep focusing on it. The point of this is it's not a step function, it is a transfer function which gets a lot of the lock accomplished at one point, but still leaves you some residual effort to work on. Anyway, you can think of these as state properties. If you want to think of fixed aspects as solids and the variable aspects as voids, you can then think of many kinds of different materials and create analogies in your mind between a project and the type of material. So on the left, we've got a type of steel, probably a stainless steel or an acidic steel, and it's a very, very dense material. And when you take a hammer and you bang on steel, you get a very strong response from it. It rings for a while, and it doesn't generally move around and squish and wiggle. It has to be really, really hot to do that. The ball bearings, on the other hand, are just as hard as individual structures, maybe even harder, but because they are not connected in the same way as the steel to the left of them, they have very, very different behaviors and properties. In some cases, they'll actually move as a fluid for you and still be able to transmit compression. They won't be any good at tension, but they will still be good at some degree of compression. They're going to have flow properties. On the other hand, on the very right side of the screen, you have an aerogel or a very porous structure. That's really good for other kinds of things. So what kinds of projects might be these? You might have a very modest line extension of a product to introduce compliance with a new video standard, which means an update to a ROM on a chip. It means a new model number and maybe a new A or something added to the front panel. That you could think of as steel, where it's almost completely controlled. You just have to do a tiny little bit of polishing on it. The ball bearings might be something where you have a product that is built like a system integrator, where you have individual elements that are constants, but you combine them in various ways very rapidly. For example, putting together cellular sites or telecommunication systems often involves thousands of sites that are built from essentially small building blocks that can be rolled out to whatever location is suitable for coverage and is available through the leasing market. The aerogels on the right are the interesting ones. This is almost the realm of R&D, where you have some constraints, but the idea is to leave as much room for thinking as possible. Clarence Kelly Johnson lived in the world of the aerogels on the right, where even the materials he built the SR-71 of had to be invented by the team in some cases. It's just an extraordinary leap from one level of technology to another one. And if you think of filling in an aerogel and making it solid enough to fly at Mach 3, that's essentially what a skunkworks operation does in some way. Anyway, you can get carried away with it, but the idea of state properties is a very useful way to communicate why some projects have different needs than others when it comes to management techniques. You would never be able to use the same machinery or flow processing for the 3 items on the screen, and no one would ever expect to, because we intuitively understand how different they are. We lack that intuitive understanding when we're talking about the domain of actual project effort, because unlike the steels and the aerogels and the ball bearings, we've never touched or felt the nature of a multi-year mega project. Unless you've lived through it, and even then it's not the same visceral sensation. So the behavior depends on the ratio and the orientation of the fixed and variable aspects. That's why I keep going back to this absolutely fundamental nature. You can think of them as X and Y on a graph if you want. The combination of them determines your project profile. This is a particularly dense graphic. There's a lot of information on this. It's included in this package mainly for the message that the cycle we're talking about of expanding with variability and then contracting to capture the potential that has been gathered. So expansion generates potential. The contraction or narrowing, the lock process, is how we capture that value and turn it into yield as the output of it. That's overlapping. It's taking place as we think about needs. We expand our view of stakeholders and possible needs and possible use cases until we get to a point of diminishing returns, and then we say, hey, what's in the net and what is it we want to keep? And as we get a better sense of those needs, we are then prepared in some sets of the subsets of the project, or perhaps all of it for simple projects, to begin exploring alternatives. How could this be done? And here we're not looking for part number 101A Model 3 Rev 2.1. We're thinking, I need a processor that is capable of taking a sensor signal and within a second or so responding to any condition it would see within a particular range. You're building the functional specification if you think of that in system engineering terms. There's a point at which you've done too much and you ought to start building the actual products. Defining the way a particular chip you're going to buy looks in the specifications, it maybe is okay if it shows someplace, but it's useless in the engineering functional requirements. You just want to say a processor capacity does this, this, and that, fits within a range. And then leave as much room. The key is each one of these stages should leave as much freedom for the next one to build as possible. You want your needs to go out and filter all of what the market may need and bring back the essential highlights of that, the Pareto subset that's important. You want your alternatives to then build on that foundation and expand back out again with the absolute potential and expectation that as you explore alternatives, you'll have a better understanding of needs. So you're not done yet with needs, but you've made a first pass that you're now building upon again. So there's generations of gain that are taking place. Then from the alternatives, the functional view of it, you can impose a solution. What device do I wish to put on my board in order to perform this function is a very natural way of seeing the progression from there is a need to control a behavior. I now need a device that does these things. The device I have selected is, and that takes you to the point solution where you can go to a mass manufacturer and get as many millions of these things made as you want. Not shown on this particular chart is the fact that once you send this to market, the opposite of this takes place. Individual users begin taking your carefully designed product and figuring out what other kinds of cool things they can do with it. And the maker-hacker community goes to work on it, including the good and bad side of that. And you'll find that things expand out the other side. We're talking about development on this side, but if it just, as long as we're here, I figured I'd just mention that. So moving forward, secret number 2 is that you need to be able to convince others of the true needs and true nature of the work so that you can get the resources and support that you need to make it happen. So your stakeholders and sponsors must understand this idea of a development difference. Without this understanding, they're going to impose limits on you based on what they genuinely think is a good idea. It'll come from whatever background and experience they have, and it may or may not be in context to your project. If it's a manufacturing-led organization, it's very likely the instincts will be manufacturing-oriented. Okay, great, anti-gravity sounds really neat. How much does it cost and how much payback will I have this quarter is the wrong kind of interaction to have on something that could be a breakthrough technology. So you have to be able to communicate what you need, but also why those needs exist. Just going in and saying, here's my specification, it's 300 slices or 300 pages of thinly sliced dead tree with lots of words on it, is meaningless to somebody if they're not connecting it to a visceral need, perhaps even one that they've experienced themselves. So there are two groups of others that you're trying to interact with. So your sponsors, like the tasks themselves, are going to remain pure to their nature. You're going to have people who are very good at the fixed side of things. You're going to have the manufacturing folks, the finance folks, the quality folks, who will support and go along with every single thing that you want to do to enhance the ability to execute efficiently and repeatably and use the standard parts lists and processes and all that. They'll love you for that. You also need a group of people who are anarchists that support you, that will support the freedom for you to go challenge things when you need to in order for the project to turn out well. One size fits all fits nothing in the development world. It may work some cases in manufacturing, but because the real world of development has so many variables in it, only a responsive process can follow that. And if Agile didn't already exist, you could invent it instantly from recognizing the disconnect between current process and what the nature of the task itself is. Agile works great when it honors the nature of the task process. So the problem in this group of others is neither of these two sponsor groups understand each other. The manufacturing people think the engineers are undisciplined and create a lot of costs. The engineers think the manufacturing people are too strict and don't give them the ability to do anything. Everybody's got a problem with finance somehow in this. And all of the groups are polarized is the point. And they tend to fall into two camps. They are either the group of people who want to do new things and challenge status quo, or the people who are anchored in past processes and find safety and comfort in the past versus the future. Depending on the culture and the leadership, you're going to be anchored either to the past or to the future as a company, and in between is going to be kind of a battle zone between groups that don't understand each other. And in many organizations, they are so siloed and so incentived as a non-system, as component parts rather than an integrated system, the incentives don't add up to the behavior you would wish as an investor or a client. Anyway, these are key alignment challenges. Every project has all kinds of needs. I don't need to list them all out here, but there's a certain set of skills that are necessary to execute any project, even if it's a relatively defined project. But when you add development, particularly significant development, where you're introducing a lot of unknowns, you have to do all of the basics, but you're now adding a substantial dynamic component. Again, for engineers and others who've been around statics and dynamics in their college or other educational programs, it's very much the difference between statics and dynamics. How big is this difference? Well, it's like the difference between shooting a rifle at a stationary target in a range where you get to do it over and over and over again and dial out every one of the variables other than perhaps your own skill, versus engaging in air-to-air combat where not only is your opponent moving around, in many cases they're actively trying to shoot you down at the same time. Why is this such a big difference? It's all about the target. If the target is staying in one place, you own all the variables, dial them in, control them, fire away, and pretty soon you ought to be able to put the slug through the dead center of the target over and over and over again. If the target is moving, though, that fixed rifle range is useless to you because critical variables are out of your control. If it's moving unpredictably, you can't even lead it and hope the two will converge at some place. So you have an additional task that requires that you gain control. So this is a new task. In addition to doing the work, it's like do the work plus figure out how to do the work. And then there's another task that says, and keep adjusting that process as you go along because you won't be able to do it once. It's going to require continuous tuning. This is very similar to find the target, close on it, lock in, and only then fire for effect. So the status quo. I've had the very great luxury of going around the world and talking to people in project management and system engineering for the better part of the last 20 years. And in the longer classes that I've taught, I've had the option of simply asking this question. And the question has the form, in your practice as a program manager, system engineer, new product development manager, anyone involved in the innovation world or in these classes, I ask them, in your practice, are you more limited in day-to-day ability by the skills and tools you currently possess, lack of them basically, or by rules that are imposed on you that don't fit the nature of the work itself? almost to a person. Man, woman, all over the world, every culture, every language, they would always come back with, I can deal with the skills and the tools. I would love to have more. It would be a wise investment for my company. But the really big problem is I have to buy this part and this part doesn't work with my system. Or I have to respond to calls this way because I have a script even when I know that the script is wrong. Or I have to do something in a particular way that makes no sense, but I have to do it because it's the end of quarter and it's important to my management scoring system. So there's all kinds of cases where the rules, the instructions, the guidance are in absolute conflict with the needs of the task itself or the needs of the individuals responsible for performing the task. This is an extraordinary investment opportunity for organizations. Simply to understand that there are two classes of methods, that misapplying one wonderful class of medicine cannot fix the factory but destroy the entirety of the remaining organization, is a profound and extraordinarily valuable realization. Anyway, that's the message on this slide. So manufacturing-derived process controls aren't the solution. There's nothing wrong with the wonderful world of lean and production technology in production. But when you have variables that are coming in constantly and uncertainties, a lot of the methods that are based on a reference against a past standard become as useless to you as a divide by zero equation would be in Excel, simply because they're invalid. You can't compare against a past case when you're doing the very first of something. So what do? We create an artificial past case in the form of requirements, and then when somebody launches the space shuttle, successfully I might add, the news media reports it as being years behind schedule and hundreds of millions or billions of dollars over cost, as though the original estimate were truth and the performance somehow were an error. And there's plenty of reasons projects grow and all kinds of stuff. But the key for us is that the manufacturing subset is this artificial case where no variability exists, or a small amount of variability as is humanly possible exists, and that's why a class of methods are able to perform there. And it also explains why when variability is the source of value, those methods that are designed to destroy it become so dangerous to an organization. So these manufacturing-derived process controls are wonderful in the manufacturing context. They're very valuable for all of the subset, every one of the molecules or particles of your developmental project, where we can anchor something to past, reuse knowledge, apply it, build on it, get continuous process improvement. We want all of those. So we want to not argue against the controls. We simply want to apply them to exactly the cells where they're beneficial. This is at best unhelpful, though, if it's implied in the wrong place. So imagine you are taking a process rule that says you must always machine this part the same way. And you take that rule set into the design studio and you say, our old product isn't selling well. It seems to be too large and too heavy when we get market feedback. I'd like you to completely redesign it, but you can't change the tooling or the manufacturing process. And your designers would then look at you like, well, what can I change? Well, you could change the color or you could change the box. And marketing pipes up and says, let's give it a new name and an ad campaign. None of those really resolve the problem, but they're coming from a false anchor to the way the product was built in the past. In other words, taking a manufacturing-derived process solution into an environment where you in fact have the need for development destroys the ability for that development to take place. Taking brainstorming into production isn't necessarily a great idea, but you will eventually ship a wheel. It'll just be a very inefficient wheel. Saying you can never make a wheel round will keep you from ever inventing one. Anyway, forcing this out of context compliance error is profoundly harmful. If you dip into the brush that's marked management process controls for manufacturing and you paint that across the entire org chart, the benefit it creates in the subset of fixed tasks is real and will be noticed fairly quickly because it has a quick turn. The damage that is caused to the creative and responsive aspects of the system will be resisted by the intelligence and the professionalism of the people for a long time. Not forever, but for a long time. And that will cause you to believe that the benefit is real and no harm is taking place, but the harm is absolutely there. It's just being built up to a point where people leave the company, they rebel, they become retired in place, or a whole bunch of other things, or they destroy the outcome of projects. So manufacturing is a special case. It's in no way bad, it's just not the generic model. So in manufacturing, the goal is to get rid of variance. Variance is evil. In innovation, the goal is to introduce strategically and to the benefit of what the market requires a degree of variance, and we call that an improvement. So you need both of these, but they're absolute opposites in nature. We have plus and minus voltages on circuit cards and have for, 20, 50 years or more. We isolate them by having a different bus. We have different voltages by having a different bus. If you think of management as having a whole bunch of tasks, some of those tasks are anchored to the management of production methodology because you can reuse all of the past reference, and some of them are attached to the future where you're using system engineering or development or innovation methods. Then the two can mix very nicely. Some of them are attached to pin A, some are attached to pin B. You can switch them on and off as fast as you want to, and you can create any image on your project display that you want. This is the essence of simultaneous excellence that I've talked about in some of the other presentations you may come across. Anyway, there's another secret that goes along with this, and this is one we'll go through fairly quickly. We'll wrap this up for you. But the secret here is to draw on an emerging body of knowledge that integrates two communities that are really one but have been artificially separated by organizational structures, professional development worlds, lots of reasons, simply the scaling of the needs. But what's happening is managing requirements is essential to development. So is getting things done. You need both, and they are kind of like the fixed and variable elements that we've been talking about all along in task nature. System engineering is very good at providing a body of requirements management practices. There's a body of these methods inside PM and virtually everyone else who's ever talked about a development methodology because it's essential to have a vision of the future you anchor tasks and decisions to. But project management, program management, really can be thought of more heavily as having all of the heavy machinery that you actually need to get things done repeatedly and efficiently, and an entire body of practitioners that are really good at executing things and planning them out. But they might need a little help with defining what they're doing. So the combination of the two of them is extremely useful. There's an emerging body of knowledge on how to effectively integrate PM and SE practices. In addition to revealing what has been known anecdotally for many decades by practitioners, it's put some hard costs on the impact of this to organizations. And when you see numbers that refer to 30 or 40% of your development expense being wasted simply because of avoidable disconnects between two internal organizations, it makes that a pretty attractive investment to go chase down in a competitive marketplace. Anyway, you can think of this system engineering, what's going to be different about the new design than the old one, as kind of a lift. The status quo is going to be different by some elevation to a new or a different level of performance. And the PM piece can kind of be, well, I'm starting here and I've got to get one of those into production in the marketplace by this date. So, hey guys, we got decisions to make, let's move out. I can't tell you what to do until I've thought about it a little bit, so I'm going to need some time. Okay, how much time do you need and how much information will I get is a negotiation that must take place continuously. Step back for a second and think about 500 years ago. There wasn't a system engineering unit. There wasn't a program management office. There was a guy with a blacksmith shop who'd make you a saddle and some new shoes for your horse if you needed them. So the idea is that all of these functions that we have artificially divided, and in some cases given professional names and careers to, really are just parts of the single innate human mind approach to creative problem solving. When we artificially separate them, each one can get good on its own, and in that case, when they're both good, the one remaining area of value that you can generate and generate leverage or exponential value from is improving the integration of the two of them. And that's especially true where the end result is an ongoing, continuous, simultaneous equation of dynamic interaction between the what is it I'm doing and how do I get it done. Well, I can't do this, but I can do that. Okay, when could we get that done? Is it satisfactory to the client? Yeah, they love it. Okay, I can get this done. Now I need to do something else. That's the dance of program management and system engineering that doesn't show up in the models or the training as often as it needs to. It's really what comes from mentoring and experience. There's a reference over on the right side of the slide to Max Q, which anyone who's been in the aeronautical community or aerospace community will recognize as the peak aerodynamic stress during a liftoff trajectory. It occurs when you're going as fast through the densest part of the atmosphere as you will. There's a point at which the atmosphere becomes denser, there's a point at which the atmosphere becomes thinner faster than your acceleration is introducing new stress. And as you pass through that point, you're basically not necessarily safe, but you passed one of the key risk components in a launch profile. You can think of the equivalent of that peak risk during the launch of a product as the point at which all of your system engineering costs are very visible to the organization, but you haven't yet really built anything that they recognize as progress. That's the point where you'll take the most heat from the organization. There is an alliance that you should be aware of that's been formed by three leading organizations. Primarily the Project Management Institute, the International Council on System Engineering have an alliance for a number of major activities, including the publication of work related to this critical interface. The MIT, Massachusetts Institute of Technology, Consortium for Engineering Program Excellence has been a major partner. So the organizations have been working together on ways to improve the integration of program management and system engineering practices. This initiative started back in 2011. It has been ongoing. I'm currently the representative for the NCOSE organization as part of that alliance, but a number of other people have had that role in the past, and I'm sure others will in the future. During my tenure, there was the opportunity to take research that had been done as a result of investments by PMI and NCOSE and MIT to look at what is actually happening throughout the world in hundreds of companies across each market, multiple markets in many regions of the world. And that research came back with some profound findings. The earlier versions of those findings have been presented internally to the two organizations. There was so much value to what had been researched and discovered that it was only natural to take it to the level of professional publication. The two organizations did so. We engaged Wiley as the publisher for this. The book's now available out there. The main things that you might want to know about relative to this presentation is it has a wonderful window into this dance between what am I doing and how do I get it done that we've been talking about. It is illustrated with case studies from multiple markets that help make the point. It talks about the type of damage and why the damage is so pernicious when you have unproductive tension between these two halves of the brain, if you want to think of it that way. That tension does nothing for the project. It is an extreme additional risk programmatically, technically, cost, and schedule that is relatively easy to avoid with some fairly basic practices. Those practices and a path to doing things better are also included in the book. So even if you've bought into this logic before, if everything I've been saying has been getting head nods and yeah, exactly, that's the way it is, you need to be able to prove it to people when you're making your case of, hey guys, I got to have some time to think about the requirements. Well, you can't have the time because we need it all for test fixes. Well, if you let me do the requirements right, you won't have as much problem in test. Oh yeah, you say that all the time. I can prove it because it says so here in this book. Oh, well, you have a book, it must be right. It's nonsense, of course, in that sense, but in some cases it gives you one more way to convey the influence you need in order to be able to do the right thing to execute a developmental effort. There is a community of project management and system engineering practitioners that is much larger than both the PMI and NCOSE organizations. NCOSE is roughly 10,000 people at this point. I frankly think roughly 10 million people, probably many more in the world, would benefit from an understanding of the basic system engineering practices and tool set and simply realization of complexity that comes from awareness of that. The Program Management Institute is much larger. There are 500,000. Numbers change constantly. It's a very, very dynamic and growing organization. But both of these organizations represent a subset of practitioners worldwide, and there's lots of other interested parties. So we needed a community for all of those parties to come together. The best solution we found to date was to launch a community on LinkedIn. There's information on the slide here that talks about that, but I wanted to point out that this community is available to anyone regardless of affiliation. You don't need to be a PMI or NCOSE member in any way to benefit from the interaction with these professionals. As a resource summary and kind of wrap up to this presentation, I've provided for you here a quick reference to the Project Management Institute website, the NCOSE website. Whether you're members of these organizations or not, you'll find that there's a lot of information on the front side of both of these organizations' websites in terms of general descriptions, background, insight. You'll also find the PMSE group reference here on LinkedIn, and you'll find information on how to contact me, Randall at eintllc.com. And you can also find my LinkedIn profile and contact me that way. So, as always, thanks for thinking. I appreciate your time. Goodbye.